Hello and welcome back to 15-Minute Math. Today we're going to talk about the Intermediate Value Theorem. I've got the statement of the theorem written on the screen already. So this is the Intermediate Value Theorem, or I usually call it IVT for short. So maybe we should say IV theorem. There we go. So here's what the theorem says. Let f be a continuous function on an interval a to b, and let m be a number such that m is between f of a and f of b. Then there exists a number c such that f of c is equal to m. That is a very wordy statement for what is actually a very simple theorem. So let's sketch a picture. To try to explain what this theorem is telling us. As usual, we're just going to draw a pretty generic function. There we go. And let's draw some interval boundaries here. Maybe we could do it in blue. We'll maybe call this A, and maybe that is B. And so that looks to be about f of A, and then B would be f of B, rather, somewhere over here. There's f of B. So let's break this theorem down. It says m is a number between f of A and f of B, and I didn't specify, where it is between those 2 points. So let's just mark off a random point just to talk about it, and then we'll maybe try to generalize a little bit more. So let's call that our m. And I'm now realizing that I forgot kind of an important statement in this theorem statement. There exists a number c where c is between a and b. Okay, so actually the way I wrote it was a little less strict than what the actual theorem says. So if you're taking notes or whatever, you can make that little addendum. C needs to be between A and B. And all it's saying is no matter what choice of m you pick, the corresponding x value will lie between your interval. So as long as you pick an m value between the function values of the 2 endpoints of your interval, then the corresponding x value is going to also be inside that interval. And it doesn't matter what m you pick, right? Like we could pick maybe m could be, I don't know, somewhere in here. And then, then the corresponding x value, again, it's in between our interval. Notice I almost randomly picked this value here, which actually doesn't fit our theorem because in the statement of the theorem it says m needs to be between f of A and f of B, and of course this point is not, so that would have been a bad choice to use. But we could kind of extend these dotted lines, and so my choices for m are anything in here, and notice that as long as I pick an m value in there, the corresponding x values are going to be between A and B, and in fact it's just going to be a pretty small subset of A and B. And so the intermediate value theorem basically just says if my function has to go from here to there, it's also got to pass every single point in between here and there, right? If this function's continuous, and let's, for the sake of argument, I'm going to make it, I'm going to redraw where my A value lies. Let's just pick our A value to be here so we can kind of dial in on what we want to talk about. So if my function goes from this y value all the way up to that y value and it's continuous, it's got to hit all the y values in between. That's kind of what this theorem says. If I'm going from some lower altitude to some higher altitude, I've got to hit all the altitudes in between. I can't jump. I don't miss steps. Okay, which that might be a duh statement, but actually, as you get more advanced, this is a very powerful statement, and it's nice that it exists because we can prove a lot of theorems with it. So it's also kind of particular to the real numbers. This wouldn't work if we were working over the integers. If we were working over the rational numbers, this is very particular to only the real numbers. So what we're going to do now is we'll look at a pretty famous example, and then that'll probably wrap it up. Okay, so the example we want to look at is, I always call it the monk on the hill problem. And here's how it goes. So let me actually draw out this scenario. So we've got a monk. There he is. And he wants to go up this hill, mountain thing. And at the top of the mountain, there's like a temple or something. He's going to go up there and he's going to pray at the top of the hill. Okay, and it's a long journey. And so let's say he starts off at 8 a.m. and then maybe he keeps going until it takes him till 8 p.m. to get up at the top of the hill to do his prayers. His prayers take a long time, and so he sleeps there for the night and then wakes up in the morning. And in the morning trek is blue. He wakes up at 8 a.m. again, and then he ventures on down the hill. You know, So maybe we should draw the black path as well. There we go. And there we are at 8 p.m. He arrives at his location. So it takes him the same amount of time, you know, on the up trip as it does on the down trip. I'm not sure how realistic that is. You'd think he'd be going faster downhill, but whatever. And so the problem is, we're going to show there is a time where he was at the same altitude on both days at the same time. So that's what we're going to try to show. And so what I'm saying is, like, let's say maybe at 3 p.m. he was here on the return trip. Well, we're looking for a time that he's at that exact same point at 3 p.m., like same time, same spot on the mountain on both days. That has to occur, and we can force that by the intermediate value theorem. So I think what I want to do is just kind of hand sketch this graph, and then we'll go over to Desmos and kind of maybe do it a little bit more, not by hand, I suppose. So here's kind of my take on this. And, you know, if you're looking for a rigorous proof, maybe this doesn't satisfy, but I think this will convince most people. And let's say the altitude change, just so we have a number to work with. It could be any number, but we're just going to say it's 6,000 feet was the altitude change. That's why it took 12 hours, because it's a big altitude change. So we'll just mark off 6,000 here. And it took 12 hours, and so there we go. That's going to be our kind of scales there. And what black is on the up trip. So let's just kind of mark off kind of a possible path here. What we do know is he starts off at, you know, on ground level, so to speak. So we'll, at time equals 0, he was at altitude 0. And then at time equals 12, he was at altitude 6,000. We don't really know much about his journey in between, but, you know, it's probably going to do something like this, right? Like, he's going to be steadily increasing in altitude. He has a burst of energy, and then he kind of levels off again, then another. So he's kind of going in bursts here. But that, of course, there's infinitely many possible paths. I just kind of picked one. And then let's draw his return path. And let's think about what we're trying to prove here. We're going to draw his return path. We know he starts here. We know at the end he's here. And in order for this to be true, let's actually talk about how this could not be true. In order for this not to be true, like these two lines could never intersect, right? Because if I draw these lines intersecting, then we found a point in time where he's at the same altitude both trips. So in order for this to not be true, I have to be able to draw this return trip without intersecting this line here. But we know from the constraints of the problem, like the monk never gets above 6,000 feet. That's the top of the hill. So it's not going to do like one of these numbers, which wouldn't even really make sense. And obviously this is a continuous function, right? I mean, he doesn't just cease to exist at certain points of time. So no matter how I draw this function, I'm going to get an intersection which forces this statement to be true, which doesn't seem like it really is applying the intermediate value theorem, but it really is. It's just kind of in disguise. Because what I want to think about is like this right here is kind of like my f of a. This right here is my f of b. And the intermediate value theorem says we have to pass through every point between f of a and f of b. And if I have to do that at some point, I have to intersect that black curve. So we can use the intermediate value theorem to justify that that has to intersect. Okay, and another way to think about that is to think about the difference function. So maybe we call this f, and we call the blue one g. Let's think about the function g minus f. So we'll just take the difference. Okay, and obviously if I take g minus f to start with, my difference is positive, right? That's definitely a positive difference. But at some point, specifically at the end, that's what we know. If we look at the end and we took g minus f, well, that's going to be a negative number. And so, again, by intermediate value theorem, if I start off positive, I end up negative, at some point I must have passed through 0. That's the only logical thing if this is a continuous function, which it is. But what's that mean when we've passed through 0? If I get g minus f equal to 0, that means there's no difference in the function. That means we found an intersection point. And so again, by intermediate value theorem, if we look at the difference function, we can force this statement to be true again. And we can look at that on Desmos a little bit. Let me see if I can get over there. So here's kind of what I've sketched out as like the up path. I think we called that the black function on my first graph, so let's make it black. Here's the down path. And then, so what I'm claiming is if I take the difference, which you can see on the left here, this third cell is the difference function. The purple function, we forced to 0. In this case, it's right in the middle. Of course, it doesn't have to be right in the middle of the interval. It could have been anywhere. It's just the way I constructed the functions. We found that 0 point. And remember, the 0 means there's 0 difference between the up path and the down path. And we'll put all three on the screen, and you can see that that is exactly what that's telling us. So that's exactly forcing that to happen. But again, the justification here, if we want to be, obviously we could just say, well, of course the blue graph has to intersect. There's no other way. Like, I got to stay in this little rectangle. I have to cross. But we can use the intermediate value theorem to justify it a little bit more rigorously. Again, if you were in kind of a proof-based class, you'd probably want to be a little bit more rigorous than what we were here. But hopefully that gives you the idea.